Hello and welcome. Today we're going to be talking about polar coordinates and complex numbers, and specifically we're going to be looking at how to sketch graphs using polar coordinates. So let's start off with a relatively easy example, just the polar equation r equals 4. So now let's just parse through sort of what this equation means in polar. Remember, r is the distance to the origin. So in this equation, notice how theta does not appear in the equation at all. So what that's saying is, that's saying that for any angle I pick, points on the graph are going to be 4 units away from the origin. So I could make a little table here with my angles and with the distance, with r, the distance to the origin. So if I pick an angle of, say, 0 radians, I'm going to be 4 units away from the origin. Where would that point be? So that's at an angle of 0, so that's along this ray here. I'd be 4 units away, so that would be right here. So if I picked an angle of pi over 2, I'd be 4 units away from the origin. So at pi over 2, that's along this ray. 1, 2, 3, 4. I'd be 4 units away from the origin. So basically, any angle I pick, I'm going to be 4 units away from the origin. One, 2, 3, 4 here at pi radians, at 3 pi over 2 radians, 1, 2, 3, 4 units away. But I mean, note I'm picking all quadrantal angles here, but I could pick anything. Like I could pick 2 radians, which is like, I don't know, like about 114 degrees. That'd put me like over right about here, and I'd be 4 units away from the origin. So basically, any angle I pick, I'll be 4 units away from the origin. So what would the graph look like? Well, the graph is just going to be all the points that lie on the edge of this circle right here. It's going to be the circle centered at the origin with a radius of 4. So notice how polar graphs they're very different from thinking about and conceptualizing points in rectangular or Cartesian form. Like if you had the equation y equals 4 in sort of Cartesian form, it would be a horizontal line where every point on the line has a y value of 4. So here in polar, with the equation r equals 4, now this graph is sort of a circle centered at the origin. All the points are 4 units away from the origin on the edge of that circle. So it's going to take some time and some experience and some practice to be able to conceptualize what a lot of these polar graphs would look like, because we're just new to sort of thinking in terms of polar coordinates. So let's try this one. R equals 5 sine theta. Let's make a table for this one where we pick some theta values and then see what r values we get. So if theta is 0 radians, 5 sine of 0 is 0, because the sine of 0 is 0, and 5 times 0 is 0. Pi over 2. The sine of pi over 2 is 1, and 5 times 1 is 5. So I can sort of plot these points as I go. So it's 0 radians. I'm going to be 0 units away from the origin, meaning I get a point at the origin. At pi over 2 radians, I'm 5 units away from the origin. 1, 2, 3, 4, 5. Be right there. If the angle is pi radians, again, I'm going to be 0 units away from the origin, meaning I get another point at the origin there, because the sine of pi is 0. 5 times 0 is 0. And then this is where things get interesting. So at 3 pi over 2, the sine of 3 pi over 2 is negative 1. 5 times negative 1 is negative 5. So now this is where I got to be careful when I plot this. So I go out to 3 pi over 2 radians, but now the radius here is negative 5, so that means that instead of counting out towards like 3 pi over 2, like along this ray, I'm going to count sort of backwards, meaning I stay on this line, but I'm going to count out 5 units in the other direction from the origin. So 1, 2, 3, 4, 5, giving me another point right there. So you'll notice that picking these quadrantal angles, I'm only getting sort of 2 points on the graph. So I could pick some other angle values to get some other points to see what this is going to look like. Like, what if I picked pi over 4? So the sine of pi over 4 is root 2 over 2, which is like very roughly 0.7. And 5 times 0.7, that'll be like 3.5. So I'm going like pi over 4 radians. I'm going to count out 1, 2, 3.5. So I could keep playing this game. Let me write this down. It's going to be 5 root 2 over 2 exactly. So I can keep playing this game to get more points. And the graph is going to eventually look like, it's very hard for me to draw, but it's going to be a circle with a radius of 2.5 units, with the center being at the Cartesian point 0, 2.5. So already we're getting some interesting results here. Like if we graphed y equals 5 sine of x, in rectangular we'd be getting a sine curve, but in polar, if we graph r equals 5 sine of theta, we're getting a circle with the origin being a point on the edge here, and then in Cartesian this point 0, 5 here, and then in Cartesian the center is 0, 2.5. Very, very bizarre. So let's look at something even more bizarre. If we change that equation ever so slightly, what's going to happen? So a good guess might be that we're going to get another circle, because we've seen the two previous examples have been circles. But we actually get something crazy here. The graph actually looks like a flower. So let me just skip ahead to the next slide for a second. So Wolfram Alpha is really useful for plotting these. So I typed in plot r equals 5 sine of 2 theta. Notice I spelled theta because I do not have a Greek keyboard, so I don't have a theta key. So I just spelled it out, literally 2 theta, just T-H-E-T-A, spelled out theta. And Wolfram Alpha is smart, so like look at the interpretation. Plot, so it understands the word plot. And then r equals 5 sine of 2 theta, look at that, it even sort of translates that. It knows that when I type in theta, I want that to be the sort of the Greek letter theta, and then it knows that, I probably want to plot this in polar. And then look at this, it gives me a graph that kind of looks like a flower petal, and that's actually what I call these graphs. That's what most people call them, flower graphs. Interesting. And then, so this point right here, that appears to be the point in polar. The radius looks to be 5, and that looks to be at an angle of pi over 4. That's what it looks like, but let's check this out. Like if I went over here to make my table here, if I picked theta to be pi over 4, would I get that back? So if theta is pi over 4, 2 times pi over 4 is pi over 2, the sine of pi over 2 is 1, and 5 times 1 is 5. So I'm getting that point at an angle of pi over 4. 2, 3, 4, 5 units away. So the graph's going to look something like that. Get that flower petal. Now, if I go back over to this Wolfram Alpha sketch, it looks like these flower petals are all equally spaced in the plane. And there's 4 of them, so it looks like there's going to be like a 90-degree swing between each of them. So if I go back over here, I bet I get another tip of a petal at 3 pi over 4 radians. And it looks like I get one at 5 pi over 4. Boom, and then it looks like I get another one at 7 pi over 4. And kind of hard for me to sketch these. I mean, it's a very, very crude sketch there of my flower. That looks a little bit better. So we're going to be spending a lot of time in class doing an investigation where we sort of try and figure out, when we switch up coefficients here and use some trig functions, what do all the graphs look like? We get a lot of these flower-looking graphs. We're going to get some graphs that look like hearts that we call cardioids. And it's all very, very interesting. So, you'll do a great job with that in class, and I know you're up for the challenge. Good luck.